Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift toward the tallest places on Earth. Places where the air grows thin and still, and the stars feel close enough to touch. Mountains rise like frozen waves of stone, each one a memory of the planet's restless heart. They are born from the slow collisions of continents, shaped by ice, carved by wind, and crowned with snow older than any city below. To look at a mountain is to glimpse deep time. They are both immovable and alive, breathing through the rhythm of erosion and rebirth. Tonight, we will wander through that silent grandeur, tracing how mountains form, how they shape the weather, and how they touch the lives of everything that climbs their slopes. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Allow your eyes to grow heavy, and let the mountains rise gently in your mind. Let's begin. Mountains are born from the slow collision of continents. Far beneath your feet, continents move at the speed that fingernails grow. Yet when they meet, their strength is unstoppable. Over millions of years, these vast slabs of rock push against each other until the crust begins to buckle and fold. What was once a flat seabed rises inch by inch, becoming the ridges and summits that crown the world. These collisions are slow but relentless, driven by the deep motion of Earth's molten mantle. The Himalayas began this way when the Indian plate collided with Asia, crushing upward the highest mountains on Earth. Each peak carries the memory of that impact, a frozen wave of stone still rising in silence. To look at a mountain is to see the moment continents met and refused to let go, turning pressure into beauty and time into height. Some mountains rise faster than they erode away. It may seem that erosion always wins, carving mountains into valleys and plains. Yet in some places, the Earth's upward push outpaces the slow work of wind and water. When tectonic forces lift the land more quickly than rain and ice can wear it down, summits grow higher even as they crumble. In the Andes, parts of the range are still climbing at a rate of several millimeters each year. The crust beneath them thickens as if breathing upward. Rivers that try to cut valleys through the rising stone find themselves trapped in narrow gorges, unable to keep up. This delicate balance between uplift and erosion shapes the drama of the landscape, where time becomes a race between the forces that build and those that destroy. Each growing mountain is a slow-motion victory of the deep earth over the endless patience of the sky. Entire mountain ranges can move across the planet over time. Mountains may appear fixed and eternal, but they are passengers on drifting continents. As tectonic plates glide across the planet's surface, they carry entire ranges with them. The rocks of the Appalachians, for instance, were born near the equator and have traveled thousands of miles north over hundreds of millions of years. The Alps, too, have migrated across shifting crust, carried like wrinkles on a moving skin. Even volcanic mountains, seemingly rooted in place, can drift if the hot spots beneath them change position. Each range carries within its layers a record of the journey, fossils of tropical seas hidden inside icy summits, hints of the worlds they once inhabited. Though the movement is invisible in a single lifetime, the continents never sleep. They glide through deep time, and the mountains move with them, crossing oceans of stone. The Himalayas are still growing taller every year. When the Indian plate slammed into Asia around 50 million years ago, it did not stop. Even today, it continues to press northward, pushing the Tibetan plateau higher and folding the crust into soaring ridges. The Himalayas rise a little more each year, roughly the width of a fingernail. Earthquakes ripple through the region as the strain builds, a constant reminder that the collision is not yet over. As the land climbs, glaciers scrape new paths across the summits, feeding rivers that sustain billions of lives below. The tallest peaks, like Mount Everest and K2, are not ancient relics but living formations, growing and shifting even as they shed stone and snow. Each centimeter gained is a breath of the planet's inner strength, a silent expression of motion that has never truly ceased. The mountains of today are still being born. The Andes were once a seabed before being lifted skyward. Long before the Andes towered above South America, their rocks rested at the bottom of an ancient ocean. Layers of sand, coral, and shell slowly turned to limestone, shale, and sandstone. When the Nazca Plate slid beneath the continent, those sediments were crushed, folded, and pushed upward into jagged ridges. Fossil shells can still be found high among the peaks, reminders that these heights were once underwater. Volcanoes erupted along the new mountain chain, adding fresh layers of lava to the rising stone. Over millions of years, the seabed became the backbone of a continent. Even now, deep earthquakes and smoking peaks mark the boundary where the old ocean floor continues to descend beneath the land. To stand on an Andean summit is to stand upon what was once the floor of a vanished sea. The Appalachian Mountains were once as tall as the Himalayas. Today, the Appalachians are gentle, forested hills that roll across the eastern United States, but long ago, they rivaled the greatest mountains on Earth. When ancient continents collided over 400 million years ago, they crumpled the crust into massive peaks as high as the modern Himalayas. Over the ages, wind, rain, and ice slowly wore them down. What remains today are the roots of that once mighty range, their deep foundations exposed and softened by time. Beneath the trees lie rocks that have been bent, baked, and twisted by unimaginable pressures. The rounded summits we see now are like old bones of a long-vanished giant. Though they seem quiet, they still tell the story of Earth's restlessness, of the endless cycle of rising and eroding that shapes every landscape. The Appalachians are a memory of mountain grandeur, weathered but enduring. The Alps are young compared to many other mountain ranges. Though the Alps feel timeless, they are geological adolescents. Formed only about 40 million years ago when Africa pressed into Europe, they are young compared to the worn-down Appalachians or the crumbling mountains of Greenland. Their sharp ridges, steep cliffs, and snow-bright peaks owe their beauty to this youth. Glaciers still carve through them, sculpting valleys and summits into shapes of dramatic grace. Because the rocks are fresh and the uplift continues, landslides and avalanches are common, signs of a range still finding balance. Within the layers of limestone and granite, fossils of ancient seashells whisper of the Tethys Ocean that once covered this region. The Alps are a living moment in Earth's long story, captured between birth and erosion, rising high enough to pierce the weather, yet still young enough to remember the sea. The Rocky Mountains formed in a surprisingly distant location. The Rocky Mountains did not rise where one might expect. Unlike most ranges that form along plate boundaries, the Rockies erupted far inland, nearly 1,000 miles from the edge of the Pacific Plate. Around 70 million years ago, a unique collision occurred. An oceanic plate slid shallowly beneath North America instead of diving deep. This strange angle transmitted force far across the continent, buckling the crust in its middle and raising peaks where there had once been plains. Later, rivers cut deep valleys through the uplifted rock, revealing layers of ancient seabed and volcanic ash. Even now, geologists study the Rockies to understand how such distant forces created so vast a chain. They are a reminder that the planet's motions can reach far beyond the edges we see, reshaping landscapes in quiet, unexpected ways that only deep time can reveal. The mountains of Antarctica hide peaks taller than the Alps. beneath Antarctica's miles-thick ice sheet lies a hidden world of mountains. Using radar and gravity mapping, scientists have discovered the Gambutsev Range, a vast chain buried under the frozen surface. These secret peaks are as tall as the European Alps and stretch for more than 700 miles across the continent's interior. No human eye has ever seen them directly. The rocks remain locked beneath ice that has persisted for over 30 million years. Their origin is still a mystery, though some clues suggest they may have formed from the collision of ancient continents long before Antarctica froze. The mountains guide the flow of ice above them, shaping hidden valleys and subglacial lakes. They are a reminder that even on the coldest continent, unseen landscapes sleep in silence, mountains that have not felt the sky in tens of millions of years. There are underwater mountains taller than Everest. Far below the surface of the ocean, where sunlight never reaches, lies a mountain range mightier than any on land. Along the mid-ocean ridge, molten rock wells up from the mantle, forming peaks that rise taller than Mount Everest when measured from base to summit. These submarine mountains stretch across the planet like a continuous scar, wrapping around Earth for more than 40,000 miles. Volcanic vents dot their slopes, releasing heat and minerals that nourish strange ecosystems in the darkness. Towering cliffs, steep ridges and valleys form a landscape few have ever seen, yet it covers more than half the planet's surface. When explorers mapped it using sonar, they realized that the greatest mountain range on Earth was hidden beneath the waves all along. It is a world of fire and water, unseen but endlessly alive beneath the sea. The largest mountain range on Earth is beneath the ocean. Stretching for more than 40,000 miles across the planet, the mid-ocean ridge forms a continuous chain of volcanic mountains that encircles the globe like a seam. Hidden beneath miles of water, it marks the place where Earth's crust is pulling apart, allowing molten rock to rise and cool into new seafloor. The ridge snakes through every ocean, crossing the Atlantic, winding into the Indian and Pacific, even threading beneath the polar ice. Though completely submerged, it covers nearly a quarter of the planet's surface. Along its crest, black smokers gush superheated water rich with minerals, creating oases of strange life in the darkness. Creatures that had never seen sunlight thrive among its vents, living on chemistry instead of photosynthesis. The mid-ocean ridge is not a single mountain, but an entire system, the beating tectonic heart of Earth's restless surface, always forming, always renewing. Some mountains lie buried beneath ice sheets miles thick. Antarctica and Greenland conceal ancient landscapes frozen in silence. Beneath their vast ice sheets, radar surveys have revealed rugged mountain ranges, valleys and plateaus that have not felt open air in millions of years. These hidden worlds were shaped long before the ice began to grow, sculpted by rivers and glaciers that vanished long ago. The weight of the ice above them presses the land down, bending the crust into deep basins where subglacial lakes still shimmer in total darkness. Scientists have detected entire watersheds beneath the Antarctic interior, flowing around unseen peaks and ridges. The ice preserves them like a time capsule, a frozen map of the world as it once was. If the ice were to melt, continents would be transformed, revealing mountains older than human memory, preserved under a white tomb of unimaginable weight and time. Volcanoes can grow into mountains in a single lifetime. While most mountains rise over millions of years, volcanoes can build themselves astonishingly fast. When magma finds a path to the surface, it begins to pile layer upon layer of ash and lava, solidifying into a peak that grows taller with every eruption. Paracutin, a volcano in Mexico, appeared suddenly in a farmer's cornfield in the year 1943. Within days, smoke and cinders filled the air, and within a single year the volcano had risen more than 1,000 feet high. By the time it went dormant 9 years later, it stood taller than the Empire State Building. Entire villages were buried in ash, yet the landscape around it became a living record of creation itself. To watch a volcano form is to witness mountain building in real time, a reminder that the forces that shape Earth are not always slow or silent. Shield volcanoes can spread wider than entire countries. Not all volcanoes reach for the sky. Some, like those in Hawaii and Iceland, grow outward instead, spreading immense sheets of lava across hundreds of miles. These are shield volcanoes, named for their broad, gentle slopes that resemble a warrior's shield resting on the ground. Mauna Loa in Hawaii is one of the largest single structures on Earth, stretching nearly 75 miles from end to end. From its base on the ocean floor to its summit above the waves, it is taller than Mount Everest. The lava that builds such giants flows easily, spreading far before cooling, creating smooth plains of black rock that harden into new land. Over time, these overlapping flows form entire islands. Shield volcanoes remind us that not all mountains are born of violence. Some rise slowly, breath by breath, as rivers of fire become solid ground beneath a quiet sky. The tallest volcano in the solar system dwarfs every mountain on Earth. On the red planet Mars stands Olympus Mons, a volcano so vast that it could swallow the entire state of Arizona. Its slopes stretch for hundreds of miles, and its summit towers more than twice as high as Mount Everest. The mountain is so large that its curvature follows the shape of the planet itself. Scientists believe it grew to such immense size because Mars lacks tectonic plate movement. The crust never shifted beneath it, so eruptions built upon the same spot again and again, piling lava higher over millions of years. The result is a gentle, sprawling giant with cliffs taller than any on Earth. From orbit, it dominates the Martian landscape, a frozen monument to the planet's fiery past. Olympus Mons is a reminder that mountains are not bound by our world alone, but by the same cosmic forces that shape them everywhere. Some mountains are made almost entirely of coral. In certain tropical regions, what we call mountains were once living reefs beneath warm, shallow seas. Over millions of years, layers of coral and shells built massive structures of limestone that were later uplifted by tectonic forces. The island of New Guinea, for instance, contains entire ranges composed of ancient coral. Fossilized marine life lies embedded in cliffs thousands of feet above the modern ocean. These mountains tell the story of seas that vanished long ago, leaving behind stone skeletons of once living worlds. Rain and rivers carve the limestone into caverns, sinkholes, and spires, creating landscapes of surreal beauty known as karst terrain. In these places, mountains are not born from fire or collision, but from the quiet labor of countless small creatures. Each grain of stone was once part of something alive, building a world that now towers toward the sky. There are mountains made of frozen water on icy moons. Far from Earth, in the cold reaches of the outer solar system, mountains rise not from rock, but from ice, as hard as granite. On Jupiter's moon, Europa, and Saturn's moon, Enceladus, the surface is frozen ocean, yet tectonic forces still twist and break it. Blocks of ice the size of cities collide and pile up, forming ridges and peaks thousands of feet tall. On Pluto, nitrogen and methane frost behave like rock, creating glaciers that flow slowly across the surface. These ice mountains gleam in the pale sunlight, their surfaces fractured and bluish, shining like glass. Some scientists believe liquid water may still flow beneath them, warmed by internal heat. If so, those hidden oceans could shelter life. These frozen peaks are reminders that even in the coldest corners of the solar system, the physics of mountains continues to sculpt worlds of wonder. Some mountains exist inside active lava fields. In the volcanic plains of Iceland and Hawaii, small peaks rise amid seas of cooling lava. These are cinder cones, born when molten rock erupts violently from a single vent, throwing glowing fragments into the air. The fragments cool as they fall, piling into steep, conical mounds. Some are only a few hundred feet tall, while others reach thousands, their sides coated with red and black ash. In places like Iceland's Holaron Field, new cones appear within years, glowing against the dark basalt that surrounds them. The air smells of sulfur and heat, and the ground trembles faintly beneath the surface. Though these mountains are small compared to great ranges, their youth makes them extraordinary. They stand as monuments to fire itself, fresh scars in the crust of a living planet, proof that Earth is still creating new summits beneath our gaze. The color of a mountain reveals its geological story. Every shade of a mountain's surface speaks of the minerals that built it and the processes that shaped it. Rusty red slopes often contain iron that has oxidized like old metal, while greenish hues suggest the presence of copper minerals. Pale cliffs of limestone mark ancient seabeds, while dark volcanic rock tells of eruptions from the deep mantle. In deserts, mountains can shimmer in pink, ochre, or violet, painted by layers of sediment deposited over eons. Some peaks change color with the light, glowing gold at sunrise and blue at dusk. Even the snow that crowns them can carry stories, tinted by volcanic ash or desert dust carried on the wind. To geologists, a mountain's palette is a language of time and chemistry. To the rest of us, it is beauty distilled into stone, the Earth's memory written in color. Some mountains are made of rock, older than the continents themselves. Deep within the ancient cores of our planet's oldest ranges lie rocks that date back more than 4 billion years, nearly to the dawn of Earth's formation. The Acasta gneiss of northern Canada, for example, formed when the planet's crust was still cooling from its fiery youth. These rocks have survived collisions, erosion, and the birth and death of entire continents. They are fragments of Earth's first crust, transformed by pressure but never erased. To hold one of these stones is to touch a relic from a time when the planet's surface was still molten and life had not yet begun. Mountains built from such ancient rock are like fossils of the Earth itself, carrying within their crystals the record of creation. They are the oldest witnesses to our planet's long and restless story. Older than the seas, older than the continents, older than memory. The oldest mountain range on Earth is nearly unrecognizable today. In South Africa, the ancient Barberton Greenstone Belt holds the remnants of the planet's first mountains, born more than 3 billion years ago. They no longer stand tall, worn down by billions of years of wind, water, and shifting crust. What remains are low hills and twisted rocks that once formed volcanic peaks and deep ocean floors. Within their layers lie microscopic fossils of some of Earth's earliest life forms, tiny traces of bacteria preserved in stone. These mountains existed when the sky was filled with volcanic haze and the oceans were green with iron. They watched the birth of continents and the arrival of oxygen. Though their summits have long since crumbled to dust, their story endures in every grain of rock. The Barberton Range is a memory of Earth before it knew trees, a whisper from a world still learning to be alive. Mountain peaks can create their own weather systems. When moist air rises along the slopes of a mountain, it cools and condenses, forming clouds that often cling to the summit. As the air moves over the ridge and descends on the other side, it warms again, creating a rain shadow where deserts can form. This process shapes entire climates. The Andes, for instance, help create the arid Atacama Desert to their west, while the Himalayas block cold winds from Siberia, warming the plains below. On smaller scales, individual peaks can summon storms of their own. Local updrafts create thunderheads that gather around the summit like a crown of weather. Even a single mountain can influence where rain falls, how winds move, and when fog forms. In this way, mountains are not only shaped by the atmosphere, they are sculptors of it, breathing life into the skies that surround them. Clouds often form and dissolve along a mountain's edge. If you watch a mountain closely on a breezy day, you may see clouds appear and vanish with surprising speed. As air flows up the slope, it cools just enough for moisture to condense, creating thin veils of mist that hug the rocks. A few hundred feet higher, the air may dry and the cloud will fade, only to form again moments later. These shifting layers are known as orographic clouds, born directly from the mountain's influence on the air. In some places, they linger in bands, drifting like scarves around the summit. To hikers, they bring sudden fog and bursts of rain. To distant observers, they make the mountain seem alive, breathing mist in and out. Each wisp of cloud is a temporary creation, a delicate interplay of wind, temperature, and shape that makes the sky dance upon the stone. Some mountains have permanent lenticular clouds shaped like flying saucers. Above certain peaks, when strong winds flow steadily across the landscape, smooth, lens-shaped clouds can form and hover in place. These are lenticular clouds, created when air rises over a mountain, cools, and then sinks again in a repeating wave. To those who see them, they often appear otherworldly, glowing pink and gold at sunset, their curved edges sharply defined. Pilots avoid flying near them because the air beneath can churn with turbulence. In places like Mount Fuji, Mount Rainier, and the Andes, these clouds can stack in layers like floating discs. They seem motionless, but inside them, air rushes in constant motion. For centuries, lenticular clouds have inspired myths and mistaken reports of strange objects in the sky. Yet their beauty is simply the breath of the planet made visible, a reminder that even still air hides waves we cannot see. Mountain shadows can stretch for hundreds of miles at sunrise. When the first light of dawn strikes a tall peak, it casts a long shadow that can extend far across the landscape, tapering to a sharp triangle, even if the mountain itself is irregular. This happens because the sun is low on the horizon, turning the entire Earth into a canvas for light and geometry. On massive peaks like Everest or Kilimanjaro, the shadow can stretch for hundreds of miles, visible as a perfect pyramid of darkness against the glowing air. Climbers often watch this phenomenon from the summit, seeing their own mountain projected across the morning sky. As the sun rises, the shadow shortens and fades, swallowed by the light. The moment lasts only minutes, but it feels timeless, as though the mountain itself were awakening, casting its first breath into the dawn before vanishing into day. You can sometimes see your own rainbow on a mountain mist. When the sun shines from behind you onto a bank of mist or cloud below, you may see a circular rainbow encircling your shadow. This is called a glory, a halo of color created by light scattering through tiny droplets. From an airplane, it can appear around the aircraft's shadow, but on a mountain, it feels deeply personal. The ring moves with you, fading and reappearing as the mist swirls. Climbers on high peaks often describe the sight with reverence, calling it the Brocken spectre. Sometimes the shadow appears enormous, magnified by perspective, as if the mountain itself were casting a luminous reflection of your presence. To witness a glory is to see sunlight turn to wonder, a brief moment when physics becomes art, and the boundary between self and landscape blurs into color and light. The air on mountains contains less oxygen but more cosmic radiation. As altitude increases, the blanket of atmosphere around Earth thins. There are fewer oxygen molecules in each breath, and the body must work harder to draw in what it needs. At the same time, the thinner air provides less shielding from the constant rain of cosmic rays that drift in from space. At the summit of Everest, radiation exposure is roughly double that at sea level. Over time, this affects both humans and technology. Pilots and mountaineers often experience higher doses simply by spending time above the clouds. Yet, in exchange for this harshness, the air offers unmatched clarity. Stars blaze brighter, and the sky deepens into a darker blue than most people ever see. Mountains bring us closer not only to the heavens we admire, but to the silent energy that fills the universe beyond them. Mountains can create wind patterns that circle the globe. When air encounters a mountain range, it is forced upward, cooling and releasing moisture. On the far side, it descends dry and warm, setting up pressure differences that ripple outward. These shifts in airflow can link together, influencing weather thousands of miles away. The Himalayas, for instance, play a crucial role in shaping the Asian monsoon, while the Andes steer the jet streams over South America. Even smaller ranges affect global circulation, guiding the paths of storms and trade winds. In the upper atmosphere, waves of air created by mountains can travel around the planet, their energy detectable from orbit. Each mountain acts like a musical note in Earth's symphony of wind, tuning the movement of air that governs climate. The peaks seem motionless, yet their presence helps conduct the rhythm of the sky itself. Mountain air carries microscopic particles from distant deserts. Every gust of mountain wind is full of stories from faraway places. Tiny grains of dust lifted from the Sahara Desert can travel thousands of miles, crossing oceans and settling on the snowy slopes of the Alps or the Andes. These airborne travelers contain minerals, pollen, even traces of microbes. When they land on ice, they darken the surface slightly, speeding the melt beneath the sun. Volcanic ash, sea salt, and forest smoke join this global dance of particles, circulating endlessly through the sky. Scientists studying mountain snow can read these layers like the pages of a diary, revealing centuries of wind, drought, and storm. Even in the most remote summits, the air is never truly empty. It carries whispers of deserts, oceans, and fires from across the Earth, proof that every breath of wind is part of a single planetary story. Snowflakes form differently at high altitude. High in the cold, thin air of mountain skies, snowflakes grow into intricate, crystalline shapes, unlike those formed closer to sea level. Temperature, humidity, and the speed of freezing all influence the geometry of each flake. At great heights, the air is often drier and colder, leading to needles, columns, and hollow prisms, rather than broad, branching stars. Some flakes even form as perfectly hexagonal plates that sparkle like glass in sunlight. As they fall through varying layers of air, their shapes change, adding ridges and facets until they settle upon the snowfields below. No two flakes follow exactly the same path, making every one a unique sculpture of the atmosphere. The snow that blankets mountains is a tapestry of countless small miracles, each crystal a frozen story of the sky's invisible breath, drifting gently toward the earth. Some mountain glaciers move faster than a person can walk. Glaciers seem timeless, but many are alive with motion. Deep within their mass, immense pressure causes ice to flow like thick syrup. Some glaciers, such as those in Greenland and Alaska, can surge forward several feet each day. A few have been known to move miles in a single year, faster than a person strolling across a valley below. The secret lies in meltwater beneath the ice, which acts like a lubricant, allowing the glacier to slide over the bedrock. As it moves, it grinds stone into fine powder and sculpts deep valleys. Even here the glacier creak and groan as fractures open and close, as if it were breathing. Though it seems cold and still, a glacier is a river frozen in time, always flowing, always reshaping the mountains it embraces, carrying their stories slowly toward the sea. Others are frozen so solid they have not moved in thousands of years. In the coldest corners of the Earth, some glaciers are locked in place, their ice so brittle and frozen that it behaves like stone. These stagnant glaciers sit in Antarctica and high in the Himalayas, unmoving for centuries. Layers of snow have compacted into dense ice, trapping ancient air within tiny bubbles. Scientists drill deep cores into them to study the atmosphere of ages past, reading their compressed layers like pages of a frozen diary. These glaciers preserve a record of volcanic eruptions, shifting climates, and even the rise and fall of civilizations that depended on distant weather. Though they appear lifeless, they hold within them the breath of the ancient Earth, sealed beneath the surface. Each bubble of trapped air whispers from a world long gone, frozen in perfect silence, waiting patiently for the warmth of human curiosity to uncover its story. Glaciers carve valleys that outlast entire civilizations. As glaciers advance and retreat, they sculpt the land into vast U-shaped valleys, smoothing and deepening everything in their path. The slow grinding of ice against rock reshapes mountains over millennia, leaving behind polished cliffs and deep basins that later fill with rivers and lakes. When the glaciers melt, the marks of their passage remain for tens of thousands of years, long after human cities rise and crumble. Many of the world's great valleys, such as those in Norway and New Zealand, were carved this way, their grandeur shaped by the patience of ice. Even now, in places where glaciers have long vanished, their fingerprints linger in every curve of the landscape. They are the architects of deep time, working not in centuries but in ages, their artistry measured in the soft perfection of a single valley floor. Some mountains act as time machines, revealing climates of the ancient Earth. Layers of rock within a mountain are more than just stone, they are pages from Earth's history. Each stratum preserves a chapter of ancient weather, captured in minerals, fossils, and chemical traces. By studying oxygen isotopes in limestone or the texture of old volcanic ash, scientists can reconstruct what the air and oceans were like millions of years ago. Some peaks in the Himalayas contain marine fossils from a time when the region was an ocean floor. Others hold layers of desert sandstone now sitting miles above sea level. To climb a mountain is to walk upward through time, from the present into the distant past. Every ridge, every outcrop, is a frozen memory of a world that once was, a record of rain, heat, and life. Mountains do not merely touch the sky, they touch the ages before it. Mountains store most of the world's fresh water as ice and snow. High in the cold air, snow gathers year after year, compressing into glaciers that hold nearly 3/4 of the planet's fresh water. These frozen reservoirs feed rivers that sustain billions of people across Asia, Europe, and the Americas. In spring and summer, melting snow trickles down into valleys, filling streams, lakes, and reservoirs. When the snow arrives late or melts too soon, drought follows. The Himalayas, Andes, and Rockies are sometimes called the water towers of the world because of how many lives depend on their steady rhythm of freezing and thawing. Each winter they lock away water in crystalline form, and each summer they release it again, a pulse that keeps entire ecosystems alive. To watch snow falling on a high peak is to see the planet quietly storing life, molecule by molecule, waiting for the warmth, that will send it flowing home. The melting of mountain glaciers can shift the weight of continents. Glaciers are heavy, unimaginably so. A single cubic yard of ice weighs nearly a ton, and entire mountain ranges can be draped in ice sheets miles thick. When these glaciers melt, the weight on the crust below them lessens, allowing the land to slowly rebound upward in a process called isostatic adjustment. Northern Europe and Canada are still rising today from the loss of ancient ice that melted thousands of years ago. As the weight redistributes, it can trigger earthquakes and subtly alter sea levels across the globe. Even gravity changes slightly as the planet adjusts. This means that as the modern world warms and glaciers retreat, continents are literally lifting their shoulders, shifting ever so slightly toward the sky. Mountains, rivers, and coastlines move in response, showing that even in thawing, the power of ice still shapes the Earth. Mountains can influence the tilt of the Earth's axis over long timescales. The rise of great mountain ranges does more than alter weather and rivers. It can subtly affect the balance of the entire planet. As massive slabs of rock are lifted high, their added weight and redistribution of mass can shift how Earth spins. Over millions of years, the formation of ranges like the Himalayas or Andes can change the wobble of the planet's axis, which in turn influences long-term climate patterns. This feedback connects the movement of stone to the rhythm of the seasons. The mountains sculpted by plate collisions may help determine ice ages and warm periods far into the future. In this sense, the slow breathing of the planet's crust shapes not only the landscape, but the balance of sunlight that reaches every hemisphere. Mountains do not just rise from Earth's turning, they help guide its cosmic dance. Entire ecosystems exist only on mountain slopes. Each band of altitude on a mountain creates a different world, with its own climate, soil, and life forms. At the base, forests thrive in warmth and humidity. Higher up, evergreens give way to meadows and shrubs adapted to thin air and cold nights. Beyond the tree line, hardy mosses and lichens cling to bare rock, where few other organisms survive. Some mountain ranges host unique ecosystems that exist nowhere else on Earth, isolated by elevation and temperature. On the slopes of Mount Kilimanjaro, strange giant groundsels rise like prehistoric trees, while in the Andes, cushion plants form dense mats that trap warmth against the freezing wind. Each altitude is a different planet stacked atop the last, a vertical journey through evolution. Mountains are not just stone, they are entire worlds layered in height, each one a separate story of survival. Some plants live nowhere else on Earth but a single peak. Isolation breeds uniqueness, and mountains are nature's laboratories of evolution. In the high Andes, a plant called the Puya raymondi grows only on certain slopes between 10 and 15,000 feet. It can live for a century before sending up a flowering stalk 30 feet tall, blooming once before it dies. On Mount Kinabalu in Borneo, hundreds of plant species exist, but are found nowhere else in the world. These isolated ecosystems evolve in secrecy, shaped by the thin air, the shifting mists, and the rhythm of temperature across the day. When climates change, these species have nowhere higher to climb. Many are already disappearing, leaving behind only the memory of their fragile kingdoms in the sky. Each rare bloom and twisted shrub is a reminder that life's creativity thrives in solitude and that every mountain peak shelters a miracle all its own. Animals evolve smaller or larger on mountains depending on altitude. High altitudes shape life in surprising ways. In cold, oxygen-poor air, animals must adapt their size and physiology to survive. Some species become smaller to conserve energy, while others grow larger to retain heat. The snow leopard, for instance, has powerful lungs and a thick coat that allows it to roam effortlessly across the thin Himalayan air. Mountain rodents such as pikas remain tiny, darting among rocks to avoid the biting cold, while yaks develop massive chests and hearts to pull oxygen from the wind. Birds that live in high places often have more efficient blood chemistry, allowing them to fly where others would faint. Over generations, the altitude molds each creature like a sculptor shaping clay. The result is a tapestry of life uniquely fitted to its elevation, a living demonstration of evolution's quiet precision in the loftiest places on Earth. Some frogs live in clouds that never reach the ground. In the misty forests of Central and South America, there are frogs that spend their entire lives within clouds. These cloud forests cling to mountain slopes where moist air condenses into constant fog. Here, tree frogs and glass frogs lay their eggs on leaves glistening with dew, and their skin absorbs the moisture of the air itself. They rarely, if ever, descend to the forest floor. The clouds provide both water and shelter, a floating world where raindrops form before they fall. The delicate balance of temperature and humidity allows these creatures to thrive in places that seem half sky, half earth. To live among clouds is to exist between worlds, and these frogs have made it home. Their gentle calls echo through mist-shrouded canopies, a chorus rising and fading like the vapor that sustains them. Birds can fly higher than any human has ever climbed unaided. While humans struggle for breath above 26,000 feet, some birds soar effortlessly far beyond. The bar-headed goose is known to migrate over the Himalayas, reaching altitudes of more than 29,000 feet, higher than the summit of Everest. It accomplishes this by taking advantage of cold, dense air currents at dawn and by having blood that binds oxygen more efficiently than most species. Other birds, such as the Ruppel's vulture, have been recorded flying even higher, gliding above 37,000 feet, where temperatures drop below freezing and the air holds only a third of the oxygen found at sea. Level. At those heights, wings beat through a world few creatures will ever touch. These birds trace invisible highways through the sky, living proof of nature's astonishing adaptability, masters of the thin, shimmering edge between Earth and the stratosphere. Mountain goats have specialized hooves that can grip near vertical cliffs. The mountain goat, one of nature's most extraordinary climbers, can ascend cliffs that seem impossible to scale. Its split hooves spread wide to balance weight, while the outer edge is hard and sharp for traction. Beneath lies a soft, rubbery pad that molds to the surface of the rock, gripping tiny cracks and ledges. Even newborn kids learn to climb within hours of birth, following their mothers up sheer slopes where predators cannot reach. Watching them leap from ledge to ledge, it seems as though gravity has forgotten them. Their balance is so precise that a misstep is almost unheard of. The high cliffs they inhabit offer both protection and perspective, a place where the wind sings constantly and the view stretches into eternity. The mountain goat's hooves are an evolutionary masterpiece, perfectly crafted for life at the edge of the sky. Some insects spend their entire lives above the tree line. Above the forests and meadows where cold winds strip away most vegetation, a few hardy insects endure. Stoneflies, snow fleas, and ice midges live among the rocks and snowfields, feeding on microscopic algae or the remains of wind-blown plants. Their dark bodies absorb what little heat the sun provides, and some produce natural antifreeze in their blood to survive the chill. They crawl across glaciers, appearing lifeless, until a patch of sunlight wakes them into motion. Because these environments change so slowly, the insects have remained almost unchanged for millennia. They are tiny survivors in a world too harsh for most forms of life, proof that even the bleakest landscapes can sustain delicate ecosystems. When you look at a snow-covered summit and imagine it barren, remember that beneath the frost, an unseen world of fragile endurance quietly persists. Certain mountain butterflies migrate across multiple altitudes each season. Some species of butterfly follow an invisible ladder through the mountains, moving up and down the slopes as the seasons shift. In the Himalayas and Andes, butterflies such as the Apollo and the painted lady rise to high meadows in summer, where alpine flowers bloom. As winter approaches, they descend to warmer valleys, tracing routes that span thousands of feet in elevation. Each altitude offers a different stage of life: eggs and caterpillars in the lower forests, pupae in cool mid-level air, adults in the upper meadows. The journey is as precise as that of any migratory bird, guided by sunlight, temperature, and the scent of distant flowers. These fragile travelers connect ecosystems from base to summit, carrying pollen between worlds. Their wings shimmer across altitudes like moving petals, reminders that even the smallest life forms navigate the grand architecture of the Earth. Trees of high altitude grow in twisted shapes because of constant wind. Where the forest meets the mountain's open slopes, trees begin to warp and bend under the unending pressure of wind and cold. Their branches grow low and thick, their trunks leaning away from the direction of prevailing gusts. This phenomenon, called krumholtz, creates strange, sculpted shapes that look like living art carved by the weather itself. Each twisted pine or spruce records years of struggle, each ring inside its trunk marking another season of endurance. The trees that survive here are smaller but tougher than their valley cousins, their bark thick and roots deep. Together they form tangled, beautiful borders between life and barrenness. Standing among them, you can hear the constant whisper of air that shaped them, a reminder that mountains are not just built by stone, but also by wind that never rests. The upper forest line changes with latitude and climate. There is a point on every mountain where trees can grow no higher. This boundary, known as the timberline, varies with temperature, rainfall, and distance from the equator. Near the tropics, trees may thrive up to 12,000 feet, while near the poles, they vanish only a few hundred feet above sea level. The position of the forest line reveals much about local climate. It shifts upward in warm centuries and descends in colder ones, marking the pulse of the planet's weather through time. Above this limit, cold and wind prevent seeds from taking root. Yet even there, low shrubs and grasses sometimes find a foothold. The timberline is not a hard edge, but a fading breath, where forest becomes sky. It is one of the mountain's most delicate boundaries, balancing life against the thin air of the high world. Some mountaintops are so high, they resemble the surface of Mars. Above 20,000 feet, the air is thin, the sunlight fierce, and the soil barren. Only a few microbes and lichens survive in this near-sterile world. The temperature swings wildly between scorching days and freezing nights, and ultraviolet radiation beats down with unfiltered intensity. Scientists studying these environments often compare them to Martian landscapes, using high peaks like the Andes Atacama Plateau or the Himalayas as testing grounds for space missions. Instruments designed for Mars rovers are first tried here, where red dust and rock mimic alien terrain. Even the colors, oxidized by dry air and sunlight, glow in rusty hues. To stand on such a summit is to glimpse another planet without leaving Earth. These extreme peaks remind us that the line between our world and others is thin, drawn only by the warmth of the atmosphere we breathe. The human body begins to change within hours of reaching high altitude. At elevation, every breath carries less oxygen, and the body must quickly adapt. The heart beats faster, and breathing deepens even at rest. Within a day, the kidneys begin producing hormones that stimulate the creation of new red blood cells. Over time, muscles grow more efficient at using oxygen, and the blood thickens slightly to carry it. Yet these adaptations come with a cost: fatigue, insomnia, and the dull ache of altitude sickness for those who ascend too quickly. High-altitude people, such as the Sherpa of Nepal and the Andean Quechua, have inherited generations of physiological adjustments that allow them to thrive where others struggle. Their bodies produce nitric oxide that widens blood vessels and improves circulation. The transformation is a quiet miracle of biology, proof that life, even human life, can adjust to almost any height the mountains demand. At extreme heights, water boils at surprisingly low temperatures. Boiling water on a mountain can be a strange experience. Because air pressure decreases with altitude, water requires less heat to turn into vapor. At the summit of Everest, it boils at only about 160 degrees Fahrenheit instead of 212. This means food cooks more slowly, tea never becomes truly hot, and climbers often find themselves drinking lukewarm water that still steams in the cold air. The same principle affects weather too, as moisture evaporates and condenses differently in the thin atmosphere. For mountaineers, understanding this change can be vital for survival. It is a small but vivid reminder that the rules of everyday life bend as we climb higher. Even the simplest act of boiling water becomes an experiment in physics, proof that altitude alters not just the body, but the very nature of heat and air. People can develop new red blood cells within days of climbing high. When a person ascends to altitude, the body immediately senses the reduced oxygen. Within hours, it releases a hormone called erythropoietin from the kidneys, signaling the bone marrow to produce more red blood cells. These cells act as tiny fairies, carrying oxygen through the bloodstream to every organ. Over days and weeks, their numbers multiply, thickening the blood and improving its ability to capture each breath of thin air. This adaptation helps climbers and high-altitude dwellers survive where oxygen levels are nearly half those at sea level. Athletes sometimes train at elevation for this reason, returning stronger once their bodies adjust. The process is an elegant dance of biology and physics, proof that life is capable of remarkable flexibility. Every heartbeat at altitude is an experiment in endurance, the body quietly rewriting its chemistry to match the mountain's quiet challenge. The highest permanent settlement on Earth sits higher than some clouds. In the Peruvian Andes lies La Rinconada, a mining town perched over 16,000 feet above sea level. It is so high that clouds often drift below its streets, and visitors struggle to breathe after only a few minutes. Yet more than 30,000 people live and work there, mining gold in thin air where water boils at lukewarm temperatures. The town has no running water or sanitation, and every step requires effort. Still, its people endure, their bodies adapted to oxygen levels that would leave most faint. Above them stretch snowfields, and glaciers below, the world feels impossibly distant. Nights are cold, days intense with sunlight that burns the skin. In this fragile place, life persists on the edge of human possibility. It is a reminder that home can exist even where air itself seems too light to sustain it. Indigenous cultures have lived in mountain valleys for millennia. Long before mountaineering or exploration, people made their homes among the high valleys and passes of the world. In the Andes, Quechua and Aymara communities cultivated potatoes and quinoa on terraced slopes, mastering agriculture at altitude. In the Himalayas, Sherpa villages thrived along ancient trade routes through the clouds. The Berbers of North Africa, the Gurum of Nepal, and the peoples of the Caucasus all shaped their lives around mountains, developing languages, music, and architecture that reflected the landscape. Thin air, steep terrain, and isolation bred resilience and deep spiritual connection. For many, the mountains were not obstacles but living presences, protectors and teachers. Traditions tied to stars, glaciers, and wind still guide daily life in these regions. To walk among such communities is to see that humanity has always belonged to the mountains, not as conquerors, but as quiet companions in their shadow. Some ancient temples were built on peaks to be closer to the sky. Throughout history, civilizations have raised their most sacred monuments on high ground, believing altitude brought them nearer to the divine. In Greece, Mount Olympus was considered the home of the gods, and temples dotted its lower slopes. In the Andes, the Inca constructed shrines atop volcanic peaks more than 20,000 feet high, where priests offered golden figures to the heavens. In Japan, Mount Fuji became both a physical and spiritual ascent, its summit a gateway between worlds. Even small hilltop sanctuaries across Asia, Africa, and Europe followed the same instinct. The higher the place, the thinner the veil between heaven and earth. Building upon a mountain was both a feat of devotion and defiance, a human gesture toward the infinite. Each ancient stair and carved altar still whispers the same message, that the soul longs to rise as surely as stone. Pilgrims once crossed glaciers to reach sacred shrines. Long before the age of mountaineering, faith drove people into some of the harshest landscapes on Earth. In Tibet, devotees walked for months across frozen passes to reach monasteries hidden among snow peaks. In the Alps, pilgrims crossed glaciers to visit shrines, such as the Great St. Bernard Hospice, a refuge standing above 9,000 feet, where monks still welcome travelers today. These journeys were acts of endurance and reverence. Pilgrims carried little, relying on faith and one another to survive storms, avalanches, and thin air. The path itself was part of the prayer. Each step, an offering of effort to something greater. Even now, modern trekkers follow those ancient routes, echoing the rhythm of thousands before them. In the quiet of high places, among snow and stone, humanity's search for meaning has always found its way upward, toward the light. Myths often describe mountains as homes of gods and spirits. In nearly every culture, mountains have been imagined as sacred dwellings of divine beings. The Greeks envisioned Zeus ruling from thunderous Mount Olympus, while in Hindu mythology, Mount Kailash is the axis of the universe, the seat of Lord Shiva. In Japan, the goddess Sengen resides atop Mount Fuji, and in Maori stories, New Zealand volcanoes are living ancestors who move and quarrel. Mountains touch the sky and vanish into clouds, a mystery that invites reverence. To ancient eyes, lightning on a summit was not weather, but conversation among gods. Even today, many peaks remain off-limits to climbers out of respect for spiritual traditions. Whether as holy mountains, protectors, or sleeping spirits, they remain bridges between the human and the divine, places where the earth reaches upward as if yearning for its own reflection in the heavens. Many ancient peoples believed mountains were the axis of the world. In mythology, the idea of a world mountain appears again and again. The Greeks called it Mount Olympus, the Hindus Mount Meru, and the Norse imagined Yggdrasil, a cosmic tree connecting heaven, earth, and the underworld. In Mesoamerica, pyramids mirrored sacred peaks, symbolizing the same connection between realms. The concept endures because mountains embody balance, stability, and the link between earthbound life and celestial order. To stand on a summit and look out in all directions feels like being at the center of creation, where the sky seems to pivot around the earth. These beliefs were not simple superstition, but intuitive expressions of cosmic understanding. Ancient peoples sensed that mountains represented the spine of the world, grounding it against chaos. Even now, we look to summits for perspective, feeling instinctively that they are both anchor and axis of existence. Some mountains were said to touch the heavens themselves. Long before airplanes or satellites, humanity imagined peaks that reached into the very realm of the gods. In Mesopotamian myth, the mountain Mashu stood at the gate of the rising sun. In the Old Testament, Moses climbed Mount Sinai to receive the law amid thunder and cloud. The Inca believed their highest summits were pathways to the afterlife. These stories gave mountains a spiritual geography, their height a metaphor for transcendence. To climb a mountain was not just to ascend, but to cross the boundary between mortal and divine. The thin air, the silence, and the nearness of the stars all reinforced the illusion that one stood at the threshold of heaven. Even today, standing on a high peak can feel like touching something infinite, the same ancient awe that turned geography into myth. Lightning strikes mountains more often than anywhere else on land. Mountains rise into the paths of storm clouds, their peaks acting like natural lightning rods. The electric charge of the atmosphere concentrates near summits, and when the balance becomes too great, lightning leaps from cloud to stone. On average, tall peaks are struck hundreds of times a year. Some, like Mount Rainier or the Matterhorn, glow with static energy before a storm, making climbers' hair stand on end. In that moment, the air hums with invisible tension. Trees splinter, rocks explode, and new paths of melted glass called fulgurites trace across the ground. Each strike is a reminder that even stone cannot resist the sky's fury. Yet from a distance, the sight is beautiful, a flash of energy linking earth and air. Lightning crowns the mountains like fleeting halos, nature's own illumination of the places closest to the clouds. Some peaks hum with natural electricity during storms. Before lightning strikes, the air around a summit can become charged with static electricity. Metal objects buzz, hair stands upright, and faint humming sounds ripple through the air. This phenomenon occurs when charged particles build up along the ridge, turning the entire mountain into a conductor. On the tallest peaks, climbers have reported hearing a soft, eerie song before the storm breaks, a chorus created by millions of ions dancing along the rock. In some cases, faint blue glows appear at the tips of metal tools or around outstretched hands, a manifestation known as St. Elmo's fire. It is both beautiful and dangerous, a prelude to a lightning strike that may follow moments later. In that instant, the mountain becomes alive with electricity, humming like a great instrument played by the sky itself. Minerals deep within mountains can generate magnetic fields. Within certain rocks lie minerals rich in iron and nickel that can align with Earth's magnetic field as they form. When heated and cooled deep underground, they capture a magnetic signature that endures for millions of years. Massive deposits of magnetite, hematite, and pyrrhotite within mountain roots can create faint local magnetic anomalies detectable by instruments. In some regions, compasses spin or drift near such deposits, misleading travelers. These magnetic records are vital to science, helping geologists trace how continents moved and where ancient poles once lay. Mountains thus act as magnetic archives, preserving the invisible whispers of Earth's shifting field. Each mineral grain becomes a compass frozen in time, pointing not north as it is now, but to where north once was. The stones remember the planet's ancient orientation long after the magnetic poles have wandered away. Certain rocks inside mountains record the movement of Earth's poles. As molten rock cools, magnetic minerals inside it align with the direction of Earth's magnetic field at that moment. When those rocks solidify within mounting layers, they lock that alignment permanently in place. By studying the orientation of these minerals in rocks of different ages, scientists can reconstruct how the magnetic poles have shifted through history. This science, known as paleomagnetism, reveals that continents have drifted thousands of miles and rotated in unexpected ways. Some ancient mountain ranges show that what is now north once pointed east or west. The very stones beneath our feet are silent maps of planetary motion. Mountains, by preserving these records, have become libraries of invisible directions. They store the memory of a world turning through deep time, where even the pull of a compass is only a momentary truth written upon a restless earth. Earthquakes can raise or destroy mountains in a matter of minutes. While most mountains rise slowly, a single earthquake can change them in the blink of an eye. When immense pressure builds along faults deep underground, it can suddenly release, thrusting rock upward or causing entire slopes to collapse. The 1960 earthquake in Chile lifted parts of the coast by more than 10 feet, creating new cliffs overnight. Conversely, landslides triggered by quakes can erase peaks that stood for thousands of years. In the Himalayas and Alaska, mountain faces have crumbled in seconds under the violent shaking. These events remind us that the same forces that create beauty also unleash destruction. The Earth's crust behaves like a living skin, cracking, healing, and reshaping itself in cycles of unimaginable energy. Mountains are born from chaos, and sometimes, with a single shudder, they return to it again. Some entire lakes have vanished because a mountain shifted. When the ground beneath a lake moves during an earthquake or landslide, water can drain away almost instantly. In China's Sichuan province, the Wenchuan earthquake of 2008 triggered landslides that both created and destroyed mountain lakes within hours. Some rivers were dammed by fallen rock, forming temporary reservoirs that later burst, while others vanished as fissures opened in the bedrock. In Iceland and Alaska, similar shifts have emptied glacial lakes in a single day, leaving behind cracked basins and stranded fish. The phenomenon is both awe-inspiring and unsettling, a reminder that mountains are not fixed but breathing structures, capable of transformation even within our lifetimes. What appears permanent can vanish overnight, reshaped by the hidden movement of the Earth's deep bones beneath the surface. Landslides can travel faster than a racing car down a mountain slope. When rock and soil give way on a steep slope, gravity takes over with terrifying speed. Some landslides accelerate to more than 100 miles per hour, tearing through forests and valleys in seconds. The largest in recorded history, in Alaska's Lituya Bay, sent a wave over 1,700 feet high crashing across the fjord. The power released by such an event equals that of a major explosion. Though they can be triggered by rain, melting snow, or earthquakes, the outcome is always sudden, leaving little warning. Scientists study these events to understand how friction and heat turn solid rock into flowing debris. In the aftermath, the landscape looks as if it has been rewritten, valleys buried and rivers diverted. Landslides are the mountain's most dramatic exhale, a fleeting moment when the weight of ages comes rushing down at once. Avalanches can release more energy than an exploding bomb. When layers of snow build up on a steep slope, each layer carries its own tension. A single crack, a shout, or a change in temperature can cause them to collapse, sending thousands of tons of snow hurtling downhill. The speed can exceed 200 miles per hour, and the pressure generated at the base can snap trees and crush buildings. The energy released in a large avalanche rivals that of small explosives. Yet within their violence lies an eerie beauty, a white river cascading in silence until it hits the valley floor, where the air fills with glittering frost. Mountains store this potential energy all winter long, invisible until unleashed. To those who study them, avalanches are both catastrophe and choreography, nature's brief but powerful reminder that even snow can move with the strength of thunder. Some avalanches create temporary airwaves that can flatten forests. As a massive wall of snow races down a mountain, it pushes a wave of air ahead of it, moving faster than the snow itself. This air blast can reach hurricane strength, snapping trees, lifting roofs, and hurling debris hundreds of feet. In the Alps and the Rockies, rescue teams have found entire forests flattened by these invisible fronts, while the snow stopped short of the trees. The phenomenon explains why even sheltered valleys can suffer destruction when avalanches strike nearby. It is not just the snow that kills, but the breath of the avalanche itself, a moving shockwave of displaced atmosphere. Afterward, the silence is profound. The forest lies in tangled ruin, and the air feels unnaturally still. It is a strange echo of the power that moments earlier swept through, unseen yet unstoppable. The snow on mountains can sing as it shifts and compresses. On rare occasions, when conditions are just right, snowfields produce an eerie humming sound as layers move and settle. The vibration resonates through the frozen crystals, creating a low musical tone that can carry for miles. Known as singing snow, it has been heard in deserts, on glaciers, and across polar plateaus. The frequency depends on the density and moisture of the snow, turning wind-blown drifts into natural instruments. Ancient travelers spoke of these voices as spirits within the ice. Modern science explains them as friction between uniform grains sliding over one another, yet the experience feels no less magical. Standing on a slope and hearing the earth sing back is unforgettable. The sound drifts through the air like a whisper from another world, proof that even silence in the mountains is never truly still. Mountain caves form when water dissolves ancient limestone layers. Many mountains hide labyrinths beneath their surfaces, carved by the slow work of water. When rain absorbs carbon dioxide from the air and soil, it becomes slightly acidic. Over millennia, it seeps into cracks within limestone, dissolving the rock grain by grain. These passages widen into tunnels, chambers, and vast underground rivers. Stalactites and stalagmites grow where mineral-rich droplets fall, creating forests of stone. Some of the world's deepest caves, such as those in the Caucasus and the Carpathians, stretch for miles under the mountains above. Each echo inside them carries the sound of time itself, dripping in rhythm with the slow heartbeat of geology. These caves are the lungs of the mountains, breathing water and air through hidden veins, forever shaping the unseen architecture beneath the peaks we see above. Some cave systems run beneath entire mountain ranges. In places like the Alps, the Dinaric Alps, and the Appalachians, networks of caves weave through the bedrock for hundreds of miles. They connect through sinkholes, underground rivers, and chambers large enough to hold cathedrals. The Mammoth Cave system in Kentucky stretches for more than 400 miles beneath the surface, with new passages still being discovered. Such systems form over millions of years as groundwater follows natural fractures, expanding them into corridors of silence. These subterranean labyrinths are often home to unique creatures, from blind fish to translucent spiders, adapted to eternal darkness. Above ground, hikers may walk unaware of the vast hollow world below their feet. Entire mountains can rest upon a delicate maze of caverns, each drip of water continuing the work that began before the first human eyes ever looked upon the peaks above. Underground rivers can flow silently through mountains for centuries. Beneath the surface of many mountain ranges, water follows unseen paths, carving its own secret geography. Rain and meltwater seep into cracks, vanishing into the limestone and granite where they gather in channels worn smooth by time. These underground rivers can flow for miles, winding through caverns older than the mountains themselves. Some resurface as springs that gush from cliff sides, while others remain hidden forever, known only by the faint sound of distant dripping. Scientists trace them with dyes and instruments, watching bright colors appear miles away days or even weeks later. In these depths, water carries whispers of the surface world, shaping stone grain by grain. The rivers move slowly, patient as sleep, etching their signature through the mountain's heart. To imagine them is to picture a planet breathing inward, its pulse flowing quietly beneath rock and darkness. Rare crystals grow deep within mountain caverns. Far below where sunlight reaches, the still air of caverns nurtures minerals into spectacular forms. Droplets of mineral-rich water evaporate slowly, leaving behind shimmering crystals of calcite, aragonite, and gypsum that twist and bloom like frozen flowers. In Mexico's Cave of the Crystals, enormous selenite pillars rise taller than houses, glowing with a ghostly translucence in the dim light. Some of these formations took hundreds of thousands of years to grow, expanding at the pace of a heartbeat. The balance of temperature and humidity must remain perfect, or the crystals will stop growing entirely. Each one is a record of patience, a sculpture shaped by time and chemistry. Deep inside the earth, where silence reigns, the mountains continue to create beauty unseen by human eyes, an underground world of lightless elegance that sleeps within the bones of stone. Precious metals often form where ancient mountains once stood. Gold, silver, and copper do not simply appear by chance. They are born from the heat and pressure that once pulsed beneath ancient mountains. When magma cools slowly underground, it releases mineral-rich fluids that seep through cracks and faults, leaving behind veins of metal. As mountains erode over millions of years, these veins become exposed, ready to be discovered by rivers or by human hands. Many of the world's greatest gold fields, such as those in South Africa and Australia, lie where long-vanished mountains once towered. Mining them is, in a sense, unearthing the ghosts of peaks that disappeared before humans existed. Each nugget of gold or trace of silver is a relic of fire and time, a fragment of the planet's deep alchemy. Mountains are not only monuments of rock, they are the crucibles where Earth refines its hidden treasures. Diamonds can rise to the surface during mountain-building events. Deep beneath the crust, at depths greater than 100 miles, carbon atoms crystallize under immense heat and pressure into diamonds. These gems remain buried for ages until violent eruptions or tectonic collisions thrust them upward. The same forces that fold and lift mountains can carry diamonds closer to the surface through volcanic pipes called kimberlites. In places like Africa and Siberia, these eruptions left behind vast deposits scattered through ancient mountain roots. Some diamonds contain tiny inclusions of minerals formed at incredible pressures, providing clues about the deep earth that no instrument could reach. Each gem is a messenger from a world few will ever see. When light passes through a cut diamond, it carries with it a story that began in darkness, born from the same upheaval that raises continents and shapes the spines of the world. The rocks of mountains can reveal the chemistry of early Earth's oceans. Long before life flourished, minerals within seabed sediments recorded the chemistry of ancient oceans. When these sediments were later uplifted into mountain ranges, they preserved a chemical fingerprint of the water in which they formed. By studying these rocks, scientists can reconstruct the oxygen, carbon, and iron levels of Earth's early seas, tracing the gradual changes that allowed life to emerge. Some mountain limestones still contain the faint imprint of stromatolites, layered structures built by ancient microbes billions of years ago. Others hold bands of red and grey that tell of the planet's first rusting, when oxygen began to fill the atmosphere. To hold such a rock is to touch the memory of the world's first oceans, trapped within stone and raised skyward. Mountains do not just reach into the heavens, they carry the story of the sea. Fossils found in mountains prove that ancient seas once covered them. High among the peaks, far from any shore, seashells and coral fossils lie embedded in stone. These remnants of marine life are silent witnesses to the fact that mountains once lay beneath vast oceans. When tectonic forces collided and pushed the seafloor upward, these fossils rode with it, preserved in limestone and shale. The Alps, the Himalayas, and the Rockies all hold shells and fish bones that formed millions of years ago under shallow seas. Fossils in these rocks reveal not only lost creatures, but also the ancient climates that shaped them. They are the perfect contradiction, proof of water found in the heart of stone. To find a seashell on a mountaintop is to realize that every peak was once a seabed, and that even the loftiest summits were born from the depths of a living ocean. Some mountains contain evidence of lost continents. Beneath the visible crust of modern continents lie fragments of vanished worlds. Within certain mountain ranges, scientists have found rocks that do not match the land around them. These exotic blocks, known as terranes, are pieces of ancient continents carried across oceans by drifting tectonic plates. When the plates collide, the fragments are welded into new mountains, preserving clues about lands that no longer exist. The Himalayas, for instance, contain rocks once part of the Tethys ocean floor, while Canada's northern mountains hold remnants of a forgotten microcontinent called Arctica. By studying their composition and age, geologists can reconstruct entire continents erased from the map of time. Mountains thus serve as living archives of Earth's migrations, holding within their layers the puzzle pieces of a planet that has been forever breaking apart and reassembling itself across deep history. A few ranges still carry traces of the supercontinent Pangaea. 200 million years ago, all the continents were joined together in a single vast landmass called Pangaea. When it began to break apart, the fractures became future oceans, and the ridges became mountain chains. Today, the Appalachian Mountains in North America and the Atlas Mountains in Africa share the same geological roots, once part of the same continuous range. Even their rocks and fossils match like separated pages of a single book. As the continents drifted apart, these shared mountains were divided, carried away to different corners of the world. To stand on an Appalachian summit is to touch the same ancient stone that forms peaks across the Atlantic. Mountains are the stitching that once bound the continents together, and through them, the memory of Pangaea endures, a reminder that every shore was once joined in a single embrace of stone. Mountains have influenced global wind and rain patterns for millions of years. When a mountain range rises, it changes the way air and moisture move around the planet. Winds forced upward cool and release rain on one side, leaving deserts in the shadow behind. Over millions of years, this reshapes ecosystems, rivers, and even the course of evolution. The Andes created the arid Atacama Desert, the Himalayas redirected the jet stream, the Rockies guided storms that helped carve North America's plains. By altering atmospheric circulation, mountains influence where forests grow and where grasslands spread. They even affect the amount of carbon drawn from the air, since rain falling on young mountains carries minerals that trap carbon dioxide in the ocean. The link between stone and climate is profound. As the land lifts, the air learns new paths, and in that constant dialogue between height and wind, the rhythm of the planet itself evolves. The rise of the Himalayas helped shape the world's monsoon systems. When the Indian plate collided with Asia, it lifted not only mountains, but entire weather systems. The growing Himalayas created a vast wall that trapped moisture from the Indian Ocean, forcing it to rise and cool into heavy seasonal rains. This process gave birth to the monsoons that now nourish millions of lives each year. The plateau behind the range acts like a giant heat engine, absorbing sunlight and driving air currents across the region. Without the Himalayas, the climate of Asia would be unrecognizable, and much of the continent might be arid desert. The very water that sustains fields and forests owes its pattern to the shape of stone. Each drop of monsoon rain is a distant echo of that ancient collision, a reminder that mountains and atmosphere are bound in a partnership that still dictates the turning of the seasons. Mountain weather can change faster than any other place on Earth. In the span of a few minutes, a mountain can transform from calm sunlight to blinding storm. Warm air rises quickly along the slopes, cooling as it meets colder layers above. Clouds form, lightning flashes, and winds shift with almost no warning. Climbers have watched blue skies vanish into snow squalls before they can descend. This rapid change occurs because mountains disrupt the smooth flow of the atmosphere, forcing air into turbulence. The peaks become engines of unpredictability, their height and temperature differences spawning storms that appear and dissolve in hours. In the Alps, weather can shift 4 seasons in a single day. Such volatility gives mountains their sense of living presence, as if they breathe weather in and out. To stand on a summit beneath racing clouds is to witness nature's swiftest transformations unfolding in real time. Some storms form and vanish within a single valley. In mountainous regions, the air's behavior is shaped by the land beneath it. A single valley can act as a cradle for weather, trapping warm air during the day and releasing it at night. When moist air rises from the valley floor and cools, sudden storms can bloom and fade within minutes, never crossing the surrounding ridges. Thunder rolls between the slopes, echoing in perfect rhythm, while rain falls on one side of a river and not the other. Locals learn to read the signs: the shape of a cloud, the scent of ozone, the stillness before a downpour. These miniature weather systems are a reminder that not all storms are vast or global. Some belong only to a single mountain, a private conversation between air and stone that begins and ends before the world beyond even notices. Entire cities depend on mountain snowmelt for their water supply. The snow that gathers each winter on mountain slopes is a vast reservoir, storing the water that sustains life below. As spring warmth arrives, it melts gradually, feeding rivers that supply entire cities. Los Angeles relies on snow from the Sierra Nevada, while much of South Asia depends on Himalayan meltwater for drinking, irrigation, and power. This delicate system depends on balance. Too little snow brings drought. Too much causes floods. Scientists monitor snowpack carefully, knowing that a shift in temperature can change the fate of millions. Every flake that falls in winter is a promise written in white, a contract between mountains and the valleys below. When it melts, that promise flows outward as rivers, turning ice into abundance. To understand the true generosity of mountains is to realize that they give life drop by frozen drop. When mountains lose snow, downstream rivers can disappear. As global temperatures rise, many glaciers and snowfields are retreating faster than they can replenish. These frozen stores of water once released steady flows through the warm seasons, feeding rivers long after the last rainfall. Now, as they shrink, streams run dry earlier each year. In the Andes and Himalayas, entire communities that depend on meltwater are beginning to feel the loss. Rivers that have flowed for centuries are dwindling into trickles by midsummer. This change affects far more than humans. It transforms ecosystems, wetlands, and agriculture across continents. The disappearance of mountain snow is silent but immense, a vanishing reservoir hidden at the world's roof. To watch it fade is to witness the unraveling of time itself. For once the ice is gone, it will take millennia to return. The mountains remember water, even as the valleys forget. Certain mountain valleys act as natural amplifiers for sound. In some high valleys, sound behaves like light in a mirror. The walls of rock and the shape of the terrain reflect and focus waves of air, amplifying even the faintest noise. A single call, a crack of ice, or the roll of thunder can echo for miles, repeating again and again until it fades into silence. Some valleys produce long, haunting reverberations that seem to come from nowhere, while others distort sound so that it feels closer than it is. Ancient peoples often believed these echoes were voices of spirits or gods answering from the cliffs. Scientists now understand that it is the acoustics of the stone itself, perfectly curved to trap vibration. Still, when you hear your own voice returned by the mountains, it feels less like physics and more like communication, a conversation between self and landscape that never truly ends. Voices can echo for minutes inside some mountain basins. In rare geological formations, echoes do not fade quickly. A single shout or bell strike can linger, bouncing between curved walls of rock for nearly a full minute. The fjords of Norway, the volcanic calderas of Iceland, and certain Himalayan valleys are famous for this phenomenon. The echo seems alive, repeating and reshaping itself as the air moves. Early travelers wrote of mountains that spoke back, their words carried across frozen lakes and amplified by cliffs. Even today, the effect feels otherworldly. Sound becomes a physical presence, filling space like mist. These long echoes reveal how mountains hold and release energy, how air and stone work together in resonance. When all falls silent again, the quiet feels deeper, as though the world itself has exhaled. Mountains teach us that even a single sound can outlive its source among their vast walls of memory. Thin air at high altitude allows light to scatter in brilliant colors. At great heights, the thinner atmosphere means there are fewer particles to diffuse sunlight. As a result, the sky appears a deeper blue, and at sunrise and sunset, colors stretch across the spectrum in vivid bands of crimson and gold. Dust and ice in the upper air refract light into halos and glories, sometimes producing rare green or violet flashes. The reduced scattering also makes stars sparkle more sharply at night, their colors pure and bright. On the highest peaks, shadows appear sharper and distances more surreal, as if the world itself has been polished by altitude. Photographers and climbers alike speak of the light as almost supernatural. It is the same sunlight we know, yet at these heights, stripped of haze and interference, it reveals its true clarity. The mountains show us light as it was meant to be seen. Raw, radiant, and infinite. Mountains are some of the best places on Earth to see the stars. Far from city lights, where the air is thin and dry, the night sky unfolds in astonishing clarity. On mountain summits, you can see more stars than most people ever imagine exist. The Milky Way arches from horizon to horizon like a river of pale fire, and faint nebulae glow where airglow and pollution cannot reach. Astronomers build observatories on high peaks for precisely this reason. The atmosphere is calmer, the view sharper, and the stars more stable for observation. On Mauna Kea in Hawaii or La Silla in Chile, telescopes peer deep into space through air that has barely been touched by moisture or dust. To stand outside at such altitude is to feel suspended between Earth and the universe, surrounded by silence and starlight. The mountains bring the heavens close enough to feel, as if the cosmos were leaning nearer to listen. Ancient astronomers used mountain peaks to study the heavens. Long before telescopes, Mountains served as natural observatories. In ancient Babylon, priests climbed ziggurats, modeled after sacred hills, to chart the movement of stars. In the Andes, the Inca aligned temples with solstices and used mounting ridges as celestial markers. Greek astronomers scaled Mount Helicon and Mount Ida to watch the skies unobstructed by haze. Even in ancient China, emperors built stone platforms on high ground to track comets and eclipses. These early sky watchers understood that altitude meant clarity, that each step upward brought them closer to the eternal rhythm above. From their vantage points, they mapped constellations, predicted seasons, and wove myths from the patterns of light. Every high place became both temple and telescope, a reminder that our desire to understand the heavens has always been intertwined with our instinct to climb closer to them. Some of the world's largest observatories sit high above the clouds. Modern science continues the ancient tradition of watching the heavens from the heights. The European Southern Observatory in Chile's Atacama Desert, the Keck Observatory atop Hawaii's Mauna Kea, and the Indian Astronomical Observatory in Ladakh all stand at altitudes where air is thin and dry. From these summits, telescopes can peer through the atmosphere with minimal distortion, capturing light from galaxies billions of years old. Engineers and astronomers live and work in thin air, surrounded by silence and stars. Above the clouds, the night is so clear that the Milky Way casts shadows on the ground. These observatories represent humanity's highest reach for knowledge, built where the sky itself begins. The same mountains that once sheltered myths of gods now host the instruments that reveal the true scale of the universe. Stone and starlight have always shared the same horizon. The tallest mountains on other planets defy imagination. Earth's peaks are impressive, but in our solar system, they would be considered modest. On Mars stands Olympus Mons, a shield volcano nearly 3 times the height of Mount Everest. Its base is so vast that it could cover the entire state of Arizona. Because Mars has lower gravity and no plate tectonics to drag the crust downward, the volcano grew unchecked for millions of years. Its slopes are gentle, stretching hundreds of miles from summit to plain. Other worlds host mountains that rise even higher relative to their size. On the asteroid Vesta, a peak called Resilvia towers across a world barely 300 miles wide. In the thin Martian air, Olympus Mons casts a shadow but stretches beyond the horizon. These alien mountains remind us that the forces shaping landscapes are universal, sculpting beauty from fire and stone wherever planets dare to stand tall. There are mountains made of metal on Mercury. Mercury, the smallest and innermost planet of our solar system, hides mountains unlike any found on Earth. Its surface, scarred by ancient impacts, holds ridges and cliffs made partly of metallic rock, rich in iron and silicate. These mountains formed when the planet's interior cooled and shrank, wrinkling the crust like the skin of a drying fruit. Some cliffs, called lobate scarps, rise more than a mile high and stretch for hundreds of miles across the landscape. Because Mercury's crust is denser and harder than Earth's, its mountains gleam in sunlight like burnished steel. Scientists believe these ridges mark the planet's gradual contraction as it lost heat from its molten core. To stand upon them would be to see sunlight reflecting from stone that once flowed like liquid metal, a vision of geology frozen in its final breath, glittering beneath an endless sky of fire. Ice mountains drift across Pluto like floating glaciers. At the edge of our solar system, where the sun is only a distant star, Pluto wears a crown of icy peaks that move slowly across its surface. These mountains are made of water ice, frozen so hard that it behaves like granite. Yet beneath them lies a sea of softer nitrogen ice that flows like syrup under its own weight. Over centuries, Entire ranges drift, pushed by the slow currents of frozen nitrogen beneath. Some peaks rise taller than the Rockies, their summits gleaming in the faint light of the sun. When NASA New Horizons spacecraft flew past Pluto, it captured these drifting giants gliding across a pale plain called Sputnik Planitia. They are mountains without roots, floating upon an alien sea, reminders that even in the coldest darkness, motion and transformation continue, shaping worlds far beyond the warmth of our own. Venus has volcanoes larger than any on Earth. Beneath its thick yellow clouds, Venus hides volcanoes that dwarf most of Earth's. The largest, Mont Mars, stands nearly 5 miles high and spans hundreds of miles across its base. Around it lie vast lava plains and shield volcanoes so broad they merge into one another, covering nearly 80% of the planet's surface. Unlike Earth, Venus shows little sign of plate tectonics. Instead, its crust seems to rise and fall as giant plumes of magma push upward from below. Some of these volcanoes may still be active, releasing heat and gas into the choking atmosphere. Recent radar data suggests changes in their shapes, hinting at ongoing eruptions. If you could stand there, the air would shimmer with heat thick enough to crush steel. These mountains are monuments to a planet forever remaking itself in fire, where even the landscape burns with unending creation. Mars holds cliffs taller than Mount Everest, stacked 3 times. Along the equator of Mars lies Valles Marineris, a canyon system so immense that it defies comprehension. It stretches over 2,000 miles long and plunges more than 6 miles deep. Deeper than Mount Everest is tall, even if stacked 3 times over. Scientists believe it formed when the Martian crust cracked as the nearby Tharsis volcano swelled with lava. Over time, landslides and ancient floods widened the chasms into a labyrinth of cliffs and valleys. Standing on its rim, you would see walls vanishing into red haze, shadows fading into a horizon that curves with the planet itself. The scale of Valles Marineris redefines what a mountain can be, transforming the landscape into a scar so vast it could swallow the entire United States. It is Mars's Grand Canyon, carved not by rivers, but by the slow tearing of a restless world. Some asteroids are shaped like miniature mountains in space. Not all mountains rise from planets. Some drift freely through space, mountain-sized fragments of rock born from ancient collisions. Many asteroids, such as Bennu and Ryugu, are roughly 1/3 of a mile tall, their peaks and ridges sculpted by eons of micrometeorite impacts. Because gravity is weak, their shapes can be jagged, resembling spinning mountains adrift in the void. Spacecraft visiting these bodies have found boulders balanced on slopes where a single touch could send them floating away. Some asteroids even rotate so fast that material drifts outward, forming faint rings of dust. To land upon one is to stand on a mountain with no horizon, where the stars never move and up and down lose all meaning. They are reminders that mountains are not confined to worlds but are scattered throughout the cosmos, fragments of creation suspended between light and silence. Scientists study mountains to understand how planets evolve. Each mountain is a record of pressure, temperature, and time. By examining how peaks form and erode, scientists can infer the inner workings of planets both near and far. The patterns of uplift and collapse reveal how heat escapes from a planet's core, how its crust thickens, and how its atmosphere responds. On Earth, the study of mountain formation has illuminated the behavior of plate tectonics, while comparisons with Mars and Venus show what happens when those processes cease. Even the icy ridges of moons like Europa and Enceladus offer clues to how water and rock interact under alien conditions. Mountains are natural laboratories, conducting experiments in physics and chemistry on scales impossible to reproduce elsewhere. Each ridge and fold tells a story about balance and change, the same forces shaping every world that spins in the darkness of space. Climbing mountains helps reveal how life adapts to extremes. High altitudes test every limit of biology. The air grows thin, temperatures drop far below freezing, and sunlight becomes harsh and unfiltered. Yet life endures. Scientists studying climbers, yaks, and even microorganisms living on glaciers have discovered remarkable adaptations. Blood chemistry changes to absorb more oxygen, while certain plants alter their metabolism to resist frost. Tiny microbes have been found thriving on bare rock near summits, feeding on minerals and light alone. Studying these survivors helps researchers understand how life might exist on other planets with thin atmospheres or frozen surfaces. Every expedition into the mountains becomes an experiment in resilience, revealing the deep inventiveness of living things. In the thin air, among stone and silence, evolution speaks in whispers, reminding us that life will always find a way, even where the world itself seems to have reached its edge. Mountaineers have reached places no scientist had ever studied before. Long before satellites and aircraft, mountaineers served as the first explorers of the upper world. Their climbs often led to discoveries that scientists could not have made from below. New species of plants and insects, rare minerals, and even meteorites caught in glaciers. On Everest, climbers collected atmospheric samples that helped reveal the composition of high-altitude air. Expeditions in the Andes and the Karakoram uncovered fossils that rewrote geological history. Even today, mountaineers gather data on glacier retreat, rock stability, and weather patterns, acting as both adventurers and field scientists. Many mountains remain so remote that only those willing to climb them can study them. Every ascent is a fusion of courage and curiosity, a partnership between human endurance and scientific wonder. In reaching higher, these explorers have expanded not only horizons, but the boundaries of what humanity can know. Every mountain on Earth is slowly changing shape. To the casual eye, mountains seem timeless, yet they are in constant motion. Wind smooths their ridges, rain cups their valleys, and earthquakes tilt their slopes. Even the weight of ice and the warmth of the sun cause daily cycles of expansion and contraction. Some peaks rise as nearby crust compresses, while others sink as erosion removes their mass. Satellite measurements reveal that no mountain stands still. Every day, the Himalayas gain a fraction of an inch, the Alps erode by the width of a grain of sand, and volcanoes breathe through subtle inflation and collapse. Though imperceptible in human lifetimes, the changes are relentless. Mountains are sculpted not once but forever, evolving through invisible rhythms of stress and release. They are the planet's great slow-motion works of art, always in flux, always being remade by the same patient hand that first raised them. Even ancient peaks are still rising, sinking, or eroding away. The oldest mountains on Earth, like the worn-down Appalachians and the ancient ranges of South Africa, may appear quiet, but deep forces continue to shape them. Beneath their roots, the mantle still moves, sometimes lifting whole regions by slow buoyancy. Elsewhere, the crust cools and contracts, pulling mountains downward into subtle subsidence. Over it all, wind and water grind away at the surface, carrying the dust of summits into rivers and seas. The balance between uplift and erosion never ends. Geologists can trace cycles where a range has risen, vanished, and been reborn in new form millions of years later. Even a mountain that seems eternal is only a phase in the planet's breathing. The Earth is never still, and the quiet grace of these ancient hills conceals a secret truth. They are still alive, changing one invisible heartbeat at a time. Some mountains vanish as fast as they are born, In regions of volcanic or tectonic activity, entire peaks can rise and crumble within human memory. The island of Surtsey, off the coast of Iceland, was born from a volcanic eruption in 1963 and immediately began eroding into the sea. Similar mountains form along ocean ridges or in desert craters, where soft ash and lava cool quickly and yield to wind and rain. Some volcanic cones have collapsed only years after their creation, leaving behind circular lakes or valleys of ash. This fleeting existence shows how dynamic Earth's surface truly is. Mountains are not all monuments of eternity. Some are sparks that flare briefly and fade. They remind us that even grandeur can be temporary, that creation and destruction are inseparable forces in nature's design. Every vanished peak adds another layer to the world's memory of transformation. The roots of mountains extend deep into the crust like icebergs. What we see above the surface is only part of a mountain's true size. Beneath every range lies a vast hidden foundation called the mountain root, composed of dense rock that sinks deep into the mantle. These roots balance the visible peaks above, much like the submerged bulk of an iceberg. As erosion wears down the summit, the crust slowly rises to restore equilibrium, a process known as isostasy. In this way, mountains seem to float upon the planet's interior, adjusting their height in response to their own weight. Some roots extend tens of miles downward, forming immense structures that mirror the peaks above in reverse. The visible mountain is only half the story. The other half lies buried in silence and darkness, pressing gently against the heat of the Earth's heart, unseen yet essential to its graceful balance. A mountain's weight can bend the earth beneath it. The immense mass of a mountain is enough to warp the crust upon which it stands. Under the Himalayas, the weight of stone pushes the lithosphere downward by several miles, creating a deep depression that supports the range like a raft. This bending is not fixed. It flexes slowly as glaciers melt. Rivers carve valleys, and new rock accumulates. The crust behaves like a flexible plate, curving beneath the load and rebounding as that load lightens. Satellites can measure these subtle shifts, mapping the way the planet adjusts under pressure. The process is invisible yet continuous, part of the great balancing act between gravity and buoyancy that governs every landscape. Each mountain, by simply existing, reshapes the planet beneath it, its mass bending the Earth into curves that ripple far beyond the summit, where the first stone meets the sky. Mountains create gravity anomalies that satellites can measure. Because gravity depends on mass, regions with tall, dense mountains exert a slightly stronger pull than surrounding plains. Sensitive satellites can detect these variations, measuring changes in gravity as small as 1 part in a billion. Instruments like GRACE and GOES have mapped these subtle differences, revealing how mass shifts as glaciers melt, rivers erode, and earthquakes rearrange the crust. The Himalayas, for example, show a measurable gravitational bulge, while nearby basins exhibit weaker fields where material has been displaced. These findings allow scientists to track water flow, tectonic stress, and even magma movement deep underground. To think that mountains can tug on satellites orbiting hundreds of miles above is astonishing. Their influence extends far beyond their peaks, shaping not only weather and land, but the invisible field that binds every object to the planet's surface. Some mountain ranges are used to calibrate Earth's satellite systems. Certain satellite instruments rely on fixed reference points to align their sensors precisely. The crisp outlines of large, stable mountain ranges provide ideal markers. The Andes, the Rockies, and the Himalayas are so well mapped that space agencies use them to test optical resolution, radar alignment, and elevation models. Because their features change slowly, these mountains serve as benchmarks for measuring sea level rise, glacier retreat, and even atmospheric thickness. Every pass of a satellite refines its accuracy against the ridges and valleys below. In a sense, the mountains have become instruments themselves, part of the global network that watches the planet's pulse. Their silhouettes, once used by early navigators for orientation, now guide spacecraft orbiting hundreds of miles above. The partnership between stone and satellite is a quiet reminder that ancient landscapes still anchor our most advanced eyes in the sky. The study of mountains has its own science called orogeny. The word orogeny comes from Greek, meaning the birth of mountains. It describes the processes that fold, uplift, and shape the Earth's crust into ranges. Scientists who study orogeny examine how continents collide, how rocks deform under pressure, and how erosion interacts with tectonic motion. Each range tells a different story: the explosive birth of the Andes, the steady rise of the Himalayas, the ancient sculpting of the Appalachians. By comparing these stories, geologists can trace the history of Earth's surface back billions of years. Orogeny connects every peak to a cycle of creation and decay, showing that mountains are not accidents but essential expressions of the planet's restless energy. The term captures both the power and the poetry of geology, naming the process by which the solid Earth breathes, rises, and dreams itself into shape. Mountains exist on every continent, even under the sea. Every corner of the planet bears the marks of uplift. From the icy ridges of Antarctica to the steaming volcanoes of Hawaii, mountains rise wherever forces meet. Beneath the oceans, vast underwater ranges like the Mid-Atlantic Ridge stretch for tens of thousands of miles, forming the longest mountain chain on Earth. Even small islands often conceal towering peaks beneath the waves, their summits breaking the surface as atolls or volcanic cones. Whether cloaked in snow or coral, mountains represent the universal language of planetary motion. They form wherever heat, pressure, and gravity find bounds. No continent, no ocean floor is free from their touch. The world's spine is continuous, wrapping the globe in stone and silence. Wherever we look, the outline of a mountain is there, shaping the horizon of every world we call home. The story of mountains is the story of our planet's restless surface. Every mountain range marks a chapter in Earth's autobiography. Their peaks rise from collision, their valleys from collapse, their stones from the cooling of ancient fire. Together, they record the ceaseless movement of the crust, the shifting of continents, and the breathing of the mantle beneath. When scientists read this story, they see a planet that has never stopped evolving. Mountains grow and fade, oceans open and close, yet the rhythm continues. Each grain of sand once belonged to a summit. Each summit will someday return to dust. The mountains are both memory and prophecy, telling us what the world was and what it will become. They remind us that stability is an illusion and that beauty often emerges from upheaval. To study them is to gauge the Earth's heartbeat, pulsing steadily beneath the stillness of stone. Every mountain holds a memory of the forces that shaped the world. Within every ridge and boulder lies a story written in texture and grain. Some rocks bear the marks of ancient volcanoes, others hold fossils of vanished seas. The minerals inside reveal the pressures they endured, the heat they survived, the journeys they made from deep within the earth to the light of the sky. Mountains are memory made solid, the planet's diary in stone. To touch one is to reach across millions of years, to feel the pulse of creation still faintly warm beneath the surface. Every peak, no matter how distant or silent, carries this memory forward. When we gaze upon them, we are not just looking at rock, but at history itself, compressed into form. Mountains do not forget. They stand as witnesses to everything that has ever moved, breathed, or dreamed upon the face of the earth. Beneath every ridge and meadow, deep under snow and stone, the earth continues its patient work. Mountains do not rush. They rise, fold, and breathing rhythms older than memory. Their world is one of pressure and silence, where moments stretch into millennia and change comes as gently as the fall of a single flake of ash. What we see as a mountain is only the surface of something vaster, the visible crest of a story still unfolding far below. As you rest now, imagine those hidden layers shifting softly in the dart. Picture the slow drift of continents, the steady hum of stone reshaping itself, the whisper of glaciers carving through valleys. Even the stillest rock carries motion within it. Each pebble on a trail is a fragment of time, weathered from peaks that once touched the stars. Mountains remind us that strength is not stubbornness but endurance, not silence but patience. They show that change need not be sudden to be powerful. What crumbles becomes riverbed. What falls becomes fertile ground. Every collapse is also creation, every ending the quiet beginning of another rise. Let that thought carry you now. The world beneath your feet is alive, vast, and kind. It moves slowly enough for you to rest within it, safely held in the calm of deep time. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let your eyes grow heavy, and let the mountains cradle your thoughts. Good night.